Hello multivariable calculus students, this is Mr. Johnson and this is the second video for section 11.2. In the first video we looked at how to show that a limit did not exist, and so in this video we're going to talk about how to actually evaluate a limit that does exist. And there are really four different methods here that I've outlined for you to try to keep organized, and I have to apologize up front that I thought that more examples that I intended to put in the notes did exist in the notes, and I have realized that the printed copy does not have that. So we will be supplementing a few examples which I promise will be helpful to see. I don't have enough here to show you each of these methods, so I've added some into our notes, and I'll explain that on the next page. With regard to the four methods, the first one is by far the easiest, and you should always do this with a limit, is to attempt substitution. So no matter if we're in single variable calculus or multivariable calculus, you want to begin limits by just the simple substitution method, which is just to plug in the value that you're approaching to see if you get an answer. If you do, you're all done, and it's a very easy approach. So it's evaluation by substitution. That would be our first method. The second method is going to be the squeeze theorem, and we've talked about the squeeze theorem over the last couple of years. The squeeze theorem is essentially the ability to take the unknown and put it in between two different values. So squeeze it in between two different values or equations that do have limits that we can evaluate, and if they're the same on either side of the unknown, then the unknown must have the same limiting value. Now, there's a few things with multivariable limits that we want to kind of focus on. Number one, if we have trigonometry, we got to remember that both cosine and sine are going to be between -1 and 1 by definition. And if you were to square them, then obviously it's going to be positive, so between 0 and 1. We'll utilize that a number of times with the squeeze theorem. The other one that is not as obvious, because we really haven't seen anything like this before with multiple variables, is that if you have the absolute value of y, by definition, that is the square root of y squared, and if you think through values that x could possibly be, you know that the square root of y squared must be less than or equal to the square root of x squared plus y squared, because you're only adding more or keeping it the same with the x squared in the relationship. So you'll see this relationship show up. You will also see the relationship show up where you have y divided by the square root of x squared plus y squared, or something like that. It's not going to maybe look exactly like that, but the same type of idea. That is between 1 and -1, because again, the x squared is only possibly dividing by more. And then you will also see the relationship show up here, which is between 0 and 1. So again, does it look exactly like those relationships? Not necessarily, but the general idea of those relationships will hold true, and I have some examples related to that. This little bit of advice, just when you're stuck, try to get rid of the ugliest part of the function. It doesn't always work, of course, but if you have some part that you're going, I have no idea what that's even going to look like, I have no idea how to manipulate that, just try to at least get rid of that portion first if possible, because maybe that's just more of a distracting element of the problem. It's hard to know. The third method is the change of variables method. We're going to use polars at times, possibly cylindrical coordinates. Obviously with cylindrical coordinates you would have a limit that would be a four-dimensional limit, so it would have inputs of x, y, and z. The polar coordinates, I'll make a note here, you're really looking for stuff like x squared plus y squared, just because we know that x squared plus y squared is equal to r squared. So if we can find stuff like that where we can make a polar substitution, the benefit of polars is that quite often we can reduce it down to one variable, and then we can use L'Hopital's rule. The fourth method is to manipulate algebraically, and we'll use any technique that we've learned in the past, clearing fractions, multiplying by conjugates, trig identities, factoring, those types of things, and I'll show you some of that as well. Okay, let's move on to the next page. All right, so on this page, let me move up to the top. We're going to begin by method 1. Method 1 is obviously the first thing you should always try, and it's also the easiest. It's just simple substitution. So if you were to plug in 1 for x and -1 for y into this problem, you want to essentially double check, does this actually work as it stands? And in this case, it does. You're going to get simply E. So that limit is done, the limit exists, and the limit is E. I have one more for you. If you simply just plug in 1 for X and 2 for Y, and then you evaluate this, let's see, we get 8 and then minus 4 plus 3 plus 4, so we are going to get a limit value of 11 for this one. So by substitution is by far the easiest. If you get a value by substitution, that is your limit, and you are set. Okay, let's take some time to get into the harder ones. So we're going to start with the squeeze theorem. Here's our first example. So we want to find the limit of this particular function, and we're going to use the squeeze theorem to do so. Now we could take the approach of looking at different paths like we did in the last video. What we're going to find is that every single path we try will give us the same value. That is not proof, by the way, because it is impossible to show every single path approaching the same particular value. So we need a different approach to prove that this limit exists. Again, the first thing you should always do is substitution. In this case, we end up getting 0 in the numerator. We get 0 in the denominator. That would be considered indeterminate. And so therefore, we're going to be stuck and we have to do something with it. Okay. Again, squeeze theorem is what we're going to try. Now, I know that sine squared of y is between 0 and 1. So I know that this is true. However, in this particular case, that is actually not going to be the thing to help me. The reason for that, let me just write this down because this will be helpful as you learn or practice, working with these. So the question is, does it help for me to use this statement, which the statement is true, by the way, that is between 0 and 1. If you were to multiply, you end up getting your unknown on the inside, which is exactly what we're shooting for. And here's the problem. I don't really exactly know how to analyze that limit. I know that obviously the limit of 0 is 0, but x squared over x squared plus 2y squared, I'm a little bit stuck. I would probably have to go back to the squeeze theorem a second time. So I'm going to erase this. We're going to take a different approach. We're going to look at the other portion of this problem. So I'm going to focus on x squared divided by x squared plus 2y squared. And I know this is positive because everything is squared. I also know the largest value is 1, and this is one of the ones that I outlined on the previous page. X squared divided by x squared is 1. That's true. And if I'm dividing by x squared plus 2y squared, the only thing 2y squared would do is to reduce that. So if x squared divided by x squared is 1, the 2y squared is only going to reduce that, but it has to be positive. Therefore, we're really stuck between 0 and 1. Now we're going to take all of this and multiply everything by sine squared y, giving us 0 is less than or equal to x squared sine squared y over x squared plus 2y squared. Again, the inside of our squeeze is what we're trying to figure out. That's the unknown. So that's exactly what we're shooting for. And so now what we can do is we can take the limit as x, y goes to 0, 0. Obviously, the limit of 0 is 0, so I'm not going to bother with that. But the limit of sine squared y as x goes to 0, 0 by substitution is 0. And so what we've done with the squeeze theorem, we've shown that this particular function, this limit that we're analyzing as x, y goes to 0, 0 of x squared sine squared y over x squared plus 2 sine y squared is also equal to 0 by the squeeze theorem. All right, so there's our first look at the squeeze theorem. Now I'm going to add in a second example of this because you do need to see this more than once. In the back of your paper packet, you have blank pages starting at page 60, and that's just extra scratch work. It's honestly, it's for stuff like this where I need to add in some additional practice in order to help you with the concept. So if you're working digitally, you can just add space. If you're working on paper, go ahead and jump right to page 60 or thereabouts, and you can add this in. Just make a note to yourself that these examples are to supplement our work in 11.2. All right, so here is our first one that I have, and we can see that the problem is a little bit ugly here, and so we're working on trying to figure out what thing we can squeeze, and we can squeeze different parts of it, but we're going to focus on looking at the sign of this ugly bit. We know that sign is in between 0 and 1, no matter what that input is. -1 and 1. We know that no matter what the input is, that is our restriction of sign. And so we're going to simply multiply this by x to the fourth, giving us -x to the fourth is less than or equal to x to the fourth sine of all of this stuff is less than or equal to x to the fourth. And we're going to take the limit as xy goes to 0, 0 of -x to the fourth, which happens to be exactly the same thing as the limit as xy goes to 0, 0 of positive x to the fourth, which both are equal to 0. Okay, so we've shown by the squeeze theorem that since both the left and the right have limits of 0, the inside must also have a limit of 0. So we can make our statement that therefore the limit as xy goes to 0, 0 of x to the fourth sine of 1 over x squared plus absolute value of y is also 0 by the squeeze theorem. All right, I have an additional squeeze theorem example for you. So here's the third squeeze theorem example, and in this case we have a very similar one that I outlined at the beginning when I was kind of going through the different methods. This portion right here mimics, not the same exact look, but it mimics the style of one of those examples I gave, where this particular set, this portion of the problem, as you look at the values is going to be between 0, because it's going to be positive, and 1. The largest value that possibly could be would be 1. And again, keep in mind, we're having to, if we were to put in x is 1 and y is 0 in this particular one, we would get 0 in the numerator, 0 in the denominator. So this is indeterminate. These all have been, and so we would want to take some sort of approach. In this case, we're going to do the squeeze theorem. So we have x minus 1 squared divided by the quantity x minus 1 squared plus y squared, and that is between 0 and 1. So we're going to take that then, and we're going to multiply that by the natural log of x. And so we have 0 is less than or equal to the original function that we're evaluating, and the natural log of x. All right, so the limit as xy goes to 1, 0 of 0 is of course 0, and of natural log of x is also 0, because that natural log of 1 is going to be 0. And so what we can state is therefore the limit as xy goes to 1, 0 of x minus 1 squared natural log of x over x minus 1 squared plus y squared is also going to equal 0 by the squeeze theorem. All right, so there you go. That's the squeeze theorem. Obviously, there's more practice in the homework as well, but I hope that just seeing a few examples there makes a little bit of sense. Okay, let's go back and we're going to take a look at example 3. So if we go back to our main notes, this is example 8. This is method 3. This is change of variables. And so in this case, we're going to use polars to evaluate. And there's a note here that you can see that says that if we use r theta for the polars, then as xy goes to 0, 0, r will go to 0 from the right side. And again, when you think about the graph of a polar and what the r value is with relation to the point xy, that should make some visual sense. But that's what we're going to do here, is to convert. So we're going to take the limit as r goes to 0 from the right. We're going to convert the limit value. And then remember, we're going to let x equal r cosine theta, and we're going to let y equal r sine theta by definition. So we end up getting r cubed cosine cubed theta plus r cubed sine cubed theta divided by x squared plus y squared is now going to be r squared by definition. And we can cancel here. We don't want to substitute yet because we want to be able to cancel this. So we're going to let the limit be r going to 0 from the right, and we're going to cancel r squared in each part here. So we're going to get r cosine cubed theta plus r sine cubed theta. Notice that we don't have any defining value for theta, so theta could be anything. But if r is 0 algebraically, then this limit will become 0. So with polars, what often happens is that certain elements of it simplify really quickly. Possibly we use L'Hopital's rule if that's a situation that occurs. But in this case, it doesn't even matter what theta is. We have an r value that's going to go to 0, and so we're going to be able to simplify really quickly there. All right, let me show you one more of those. All right, so what we have here is another situation where the x squared plus y squared is part of the problem, and so I want to point out that that's often a case where we're going to look at polars or look at evaluating with polars. So we're going to take the limit as r goes to 0 from the right side, and we're going to convert to r squared and r squared. Now we get, if by substitution, we end up getting 0 in the numerator and 0 in the denominator. And so we are going to apply L'Hopital's. We're down to one variable. We can do this now. So by L'Hopital's rule, we have the limit as r goes to 0 from the right side of cosine of r squared times 2r, because of the chain rule, divided by 2r. We can obviously cancel the 2r. So we have the limit as r goes to 0 from the right of cosine of r squared, and cosine of 0 is going to be 1. So again, with polars, pretty fast process. We're able to simplify. Again, if you get down to one variable and it's a L'Hopital candidate, then you can use L'Hopital's rule. All right, let's move on to method 4. Now in your notes, you do not have any for method 4. Again, this was for some reason left off when I got these printed for you. So again, just please add this example along with the other ones I've given you as just some supplement to what we're studying here. This is going to be to manipulate algebraically. So what we're looking for here is, okay, by substitution, we end up getting 0 in the numerator, we get 0 in the denominator, so we have to do something with it. The challenge is, okay, how do you know without me telling you to use algebraic manipulation? You can think through elements of the squeeze theorem, you can think through possible change of variables, but what you're going to land on here is that we're going to need to factor this one and cancel in order to simplify and evaluate. So in the numerator, we can factor this numerator to be 2x plus y times x minus y. And if we were to just distribute that out, I'm just double checking, we would get the values of the numerator there. And then in the denominator, we would have x minus y and x plus y from the difference of squares. So we're able to cancel the x minus y. So we have the limit as x, y goes to 1, 1, and it is of 2x plus y over x plus y, and we then evaluate by substitution. So if we're going to plug in, excuse me, 1 for x and 1 for y, we get 3 divided by 2. And so algebraic manipulation by factoring, by clearing fractions, by using the conjugate, those types of things is a good thing to keep as a technique as well. I have one more of those for you. So here's another limit by algebraic manipulation. In this case, if you remember way back to, and by the way, if you were to plug in 2 for x and -4 for y, you'll get 0 in the numerator, 0 in the denominator. So again, we're having to do something with this in order to evaluate it. So way back, you've done factor by grouping. It's a concept that was probably originally taught in Algebra 2, I'm guessing. Factor by grouping is where you sort of analyze this in two parts. You analyze the first portion, then you analyze the second portion, and your goal is to try to get a similar factor in each by factoring out a value just in those two terms there. So when we look at, for instance, x squared y minus xy, we could factor out a y and get x squared minus x. And then in the second two terms, we have a factor of 4 that will give us x squared minus x. So again, this is factor by grouping. You're grouping or you're factoring in groups. The numerator then stays the same for the moment. Oops. So you have xy approaching 2, -4. We have y plus 4 in the numerator. The denominator, however, you can then factor based on your groupings. So it looks something like that. And this allows us to cancel y plus 4. And so we're left with the limit as xy goes to 2, -4. And we have 1 divided by x squared minus x. And if x is 2, we end up simplifying to 1/2. So that's going to be our limiting value. All right. I hope that's helpful with regard to the 4 different techniques. Obviously, there could be other techniques that we could use. I'm just trying to help you stay as organized as possible as you go through. So again, the first thing you should always try is by substitution. The squeeze theorem was method number 2. That is a pretty common method. Number 3 was to change your variables, and number 4 was to manipulate algebraically. Keep in mind that you should always do the substitution first, but the other 3 doesn't necessarily mean you should do them in that order. But I just wanted to show you the 4 main methods in order to evaluate these limits. Okay, that's it for this video. The next one will be on continuity. Thanks.